Hi everyone. So today we're going to talk about chirality. Chirality. This is out of Thomson 6.4, and it's actually one of the more important sections that's going to both tell us how does quantum electrodynamics conserves chirality, sorry, and how this chirality is going to play a role also in both being a conserved quantity, also in quantum thermodynamics, which is what we're going to talk about next, the quarks inside protons and neutrons. And then it's also going to apply to the weak force, which is where we're going to aiming towards in order to get to the Higgs boson eventually. Okay, so let's talk about what we just found out in this chapter, right? For the electron-positron annihilation. So remember from last time, I don't know if you can see this. Actually, no, you guys can't see this. Okay, I'll use my mouse instead. Okay, for electron-positron annihilation, right? We only have to calculate 4 of these Lorentz invariance matrix elements because, right, the right and the left of these stuff, right? So you have this matrix element MRL, and then you could have a MRR, right? But we found that these combinations are actually 0 from these long calculations that you guys did last homework, okay? And then similarly for the positron and for the positron and also for the muons that's coming out. So there's only actually 4 different matrix elements we have to calculate, and 2 of them are actually identical. I think this is the RL to RL, and then LR to LR. So when you don't exchange the helicity between the particles, that gives you the positive cosine theta. When you do exchange the helicity with the incoming and outgoing, so R to L and then L to R. Right, let's draw that explicitly, right, like that. Right, that's when you end up with the negative cosine theta in your matrix element calculation. Okay, and in calculation of helicity conservation, right? So think about this as kind of like a conservation of helicity. Okay, this only works in the high energy limit. So remember, we had to make it so that E is much bigger than M in order for us to do this calculation. Okay, so in this section, we're going to talk about chirality. Okay, it's much less intuitive, and it's actually, I think, historically people use helicity first, right, and figure out, oh, is there something that I can use in order to figure out that there's something that's conserved in all these electromagnetic interactions, so that we can actually have a calculation that actually works no matter what the energy of the incoming and outgoing particles are. Okay, so this is more of a, you know what the answer is supposed to be, right? And then now we're just going to have to make up some operators and some algebra in order for us to satisfy that. Okay, all right, so this is where chirality came from. Okay, and like, helicity is sort of still kind of a physical word. Chirality, I think they chose it, right? The chiro of a particle is kind of a symmetric pairing, but it's meant to be what is it called? Not clear. I think there's a fancier word for that, on purpose, so that we don't associate this operation with something that's more physical. Okay, because it's just really math that we're doing, that we found that is one of the symmetry in quantum electrodynamics. Okay, so what we're going to do is going to start off with just making up a new gamma matrices. This has 4 of them is not enough. Let's have a 5th one. Okay, we skip gamma 4 because gamma 4 will be a little confusing, because now you're thinking, oh, is this the spinor index or is it the Lorentz index, right? So we use gamma 5 is just so that it's different from, you don't want gamma 0, 1, 2, 3, 4, right? You don't want it to have like just to make it a little bit different. Okay, and gamma 5 is defined to be I times all the gamma matrices together. And if you do this matrix multiplication, then you end up with this, the ones in the off diagonals on the upper half, upper right, and then ones in the off diagonal on the lower left. Okay, so essentially it's just that identity matrix in the upper right and the lower left, right, where these identity matrices are 2 by 2 matrices. Okay, which then the whole thing is a 4 by 4. Okay, so since this gamma matrices is defined by other gamma matrices, right, they will satisfy the same algebra. So this is like the fancier word for algebra, where by algebra I mean all of the mathematical construction works the same, except you have a different name for things. Okay, and this is more of an abstract term. Abstract, by algebra I mean the abstract meaning of algebra, as opposed to actually y equals mx plus b type of algebra. Okay. Okay, and then you guys will get to play around to show that it's satisfy the same algebra as the other gamma matrices, which is this, that whenever you square a gamma matrix, where you end up with the identity, it is Hermitian, meaning you take the complex conjugate and then you adjoin it, you get the same thing. And then they also anti-commute with each other, right? Just to write this out a little bit more clear, right? Gamma mu plus gamma mu gamma 5 equal to 0. So if you can't switch, so you switch the order of these with the addition instead of subtraction. Remember, commutator is when you have a subtraction between the two matrices. Sorry, subtraction between the product of two matrices, and if they are the same, that means you can actually, they add up to 0. That means you can actually switch the order of these matrices without changing anything. But these matrices anti-commute, so when you switch the order of them, okay, you end up, instead of being the same matrix, you end up with a negative of the same matrix instead. Okay. Okay. So the eigenstates that we derive for the helicity operator, right, are going to share the same eigenstate as gamma 5 because they obey exactly the same algebra. So therefore, right, gamma 5, right, operated on, let's say, the helicity up, or in this, R, right, helicity R eigenstate will be the same thing, will give you the same eigenstate, but with a positive sign. But if you act on it with the left helicity, then you end up with a negative. Okay, and the antiparticle behaves similarly, except the sign is different. So where the right gives you a minus, right, the left gives you the plus, right? Okay, so the algebra here is exactly the same as helicity, where helicity is this p dot sigma thing, but right now we're going to see if we can get this to work in the non-high energy limit, meaning we just let energy be anything we want. It doesn't have to be much bigger than that. Okay, so right now we're just doing algebra. We haven't done any high energy limit or anything like that. Okay, so what we're going to do is we're going to change this labeling. Okay, where instead of, so this only works in the high energy limit, right? Okay, what we're going to do is we're going to undo that by just changing the label. Let's just call the right-handed helicity, U sub R. This is the reason why Thomson and everyone else who writes a particle physics textbook stays away from labeling these eigenstate spinors U sub R's, U sub left, until this point. Okay. And then the left-handed helicity, which is labeled with this down arrow, right? We're going to label that as U sub L. Okay. Similarly, the up type antiparticles will be V sub R, and then the down type helicity antiparticles will be I think that's a typo. Okay, V's of L. Okay. Okay. All right. So with that, okay, what we can do is then, well, since now we define these gamma matrices, we can just do a direct substitution where instead of calling, this use of up, we're just going to call them use of R's. Okay. In fact, what happened is that the right helicity eigenstate, right? If you add gamma 5 on it, you end up with a positive 1, just like helicity. But now we are not going to make the assumption of E much bigger than M, okay? Right. Similarly, right, the particle, the left chiral particles, right, will have an eigenvalue of -1, and they'll have the eigenstates of use of left, or the left chiral spinner, okay? Similar for the antiparticle, except the right chiral antiparticle will have an eigenvalue of -1. The left chiral will have a eigenstate of +1 instead. Okay. So in changing these labels, right, the solution doesn't change, right? We still have these same solutions. Okay, where the right chiral spinners is going to be some normalization, and this normalization doesn't need to be taken to the high energy limit anymore. In fact, this I think is, it's actually P over E plus M, right? Right, all these normalization. I think the normalization outside is actually square root of E plus M. Sorry, so it's not just a square root of E. Okay. Okay. So make sure you just look those over. This the same thing we had in chapter 4, but right now we're not taking the high energy limit as we did with the helicity. Okay. All right. So what we're going to talk about next is that is there a way for us to represent any state using this type of right and left chiral eigenstates of our solution. Okay. So just to remind you, just to connect this to a analogy, so this is kind of silly, right? Remember that when you have a vector in your algebra class, and now I mean algebra as in like the non-abstract algebra, right? So we have some vector here, right? Okay. We call this like the x-axis, we call this the y-axis, stuff like that, right? What we can do is we can do a projection along the x-axis. So let's call this vector, let's not call it v, let's call it r vector, right? That way it's not confusing with the antiparticle stuff. Okay, so the projection along the x-axis, right, we call that the x component, and then we have the projection along the y component, we call it ry, right? Okay, right. So there's a little bit of more that usually people don't talk about when you start this, right? So x and y, right, they are what's known as orthogonal bases of your vector space. Okay. Okay. Why is it called that? Because if we're dealing with anything that's on the xy plane, right, that's your space. That's where all your stuff is happening. Okay. By writing a vector, let's say r, right, with some piece along, well, let's call that rx since I already called it rx, along the x direction, plus some piece along the y direction, you can go to any point, right, in your xy plane. Okay. Okay. Right. So what we want to abstract out of this is that these are your bases, the x and y hat unit vectors. Okay. Right. These are the components, right, of each of those, from each of those bases, and the xy plane is basically your vector space. Okay, where can your stuff go? Okay, okay. So we're going to do something similar here, and if you don't follow kind of the more abstract part of it, it's okay, but just follow the the techniques, and then if you did this 100 times, then you may get used to it. Okay. Just kidding about the 100 times, maybe 3. Okay. So what we're going to do is we're going to define a new set of operator called PR and PL, and the P stands for projection. So we're going to project things into the right-handed chirality axis, and the left-handed, the left chiral basis using these operators. Okay, so the analogy is that you're basically doing the same thing as by projecting your arbitrary vector down to the x-axis, you're projecting it to the x basis, and by projecting to the y basis, the y vector down, you can project that to the y basis. Okay. Okay. And we're gonna just tell you what it is. Okay. So PR is just gonna be 1/2. Okay, just for normalization sake, 1 plus gamma 5, and then PL is going to be the same thing, 1/2, 1 minus gamma 5. Okay. Okay. If you compute this in the Pauli-Dirac representation, which is all we've been using in this book, okay, if we switch that up on you, we'll let you know for sure. Okay. PR is going to be 1/2 because of the 1/2 in front, and it's going to be basically the identity matrix plus gamma 5, right? So this is the red is the identity, right? The green are the gamma 5s, right? Because gamma 5 is up here. Yep, right, right, same thing. Okay. Okay. PL, well, guess what that is, right? You have the identity matrix, go over here, okay, and then you have negative of gamma 5, right? Oops, include that one. Okay. All right, so let's check the functionality of this projection operator. Okay, so let's see what it does to an arbitrary chiral state. Okay, all right, so that was the plan. Okay, and you get to practice. I'm going to do this with the right, and you're going to get to practice this with the left. Okay, so what we're going to do is we're going to apply this operator on something maybe that has an amplitude right, u right. Okay, so this is the 4x4 vector spinner. Okay, this is just some number in front that tells you how much is it contributing. So like the analogy of this is like, Rx, right? Right, from our low analogy. Okay, right, plus some y component, or right, RL, UL. Okay, right. So when you do this, right, what happened is that, right, you have PR, AR, UR. Oops. Yeah, let's just keep it abstract for now. And then PRAL, UL. Okay. Okay. So, oops, what's over here? Okay. So this is gonna turn into a little bit. So I'm gonna do is I'm gonna deal with this first. Well, actually, yeah, let's deal with the right one first. Okay. So this is just a number, so we can just pull that in front. Okay. Right. So we're doing PR, which is 1 along the diagonal, and then we have a bunch of zeros. 0, 0. Oh, oops, there's a 0 there. Okay. And we're acting on this with use of R, which is the thing up here, right? S, C, S, C, S, okay? with phi on the second and the third. CS, CS, EI phi, EI phi. Okay. Right. I'm just going to deal with this piece first. Okay. Right. And I'll deal with the other piece yet. Okay. So we still have AR in front. Okay. If you do this multiplication, right, you're going to end up with, right, okay, right, basically 1 times C, 1 times C, you get 2 times C here, okay, and then you get 1 times S, EI phi, and you get another 1 times S, EI phi. You get basically 2 EI phi there, okay. I think now you're seeing why there's a 1/2 in front, which I forgot actually, right? AR 1/2. Okay. Okay. Now similarly, you're going to get 2 times C here, and then you're going to get 2 times EI phi there. Okay. The 2's actually cancels out, so you end up with AR, right? C. Oops, I forgot the S here. S. S EI phi, and then C. S EI phi. So this is exactly UR, right? Cool. So the projection on the R component gives you exactly what the R component is with this, kind of this amplitude factor. Okay. All right, and now let's do the other one. Okay. Let's do that in red. Okay. So now, right, how we deal with this one? Oops. Red. Let's do that in red. Okay. So PR AL UL, right? The AL just goes in front, and then PR. This time I'm going to remember the 1/2, right? So it's going to be 1, 1, 1, 1, 0. Since it's PR, oops, right? 1, 0, 1, 0, 0, 0, 0, 1, 1, 0, 0. Okay. Now we're going to act on this with the UL, which is a different spinner. So it's minus S, so SC, SC, and then minus on the top and the bottom. SC, SC, minus on the top and the bottom. And I think it's the EI phi connected to the cosine this side. Okay. I mean, a lot of this is not going to matter, but let's just write everything out. Okay, you have AL over 2, right? So do this multiplication, right? You get minus S, you get plus S, right? You get 0 on the first component. You get plus C I phi, and then you have minus C I phi. I think you guys are seeing what's happening here, right? For the third component, right, we get, well, I'll write out S minus S plus S, also 0. And then the fourth component, right, you get C EI phi minus C EI phi. That's also going to be 0. So PR, right, the projection on to the right Kairos axis, right? AL, well, let's just put that AL in front. Okay, this is a number, right? UL equal to 0, right? So therefore, must be that in general, right, use projecting something that only have a left chirality onto it is going to be 0. Oh, and up here, forgot this stuff up here. Okay, this is, right, AR, PR, UR, right? So therefore, right, PR, UR gives you the same thing back, where if you project to the different bases, you get 0, right? So the analogy of this I want you guys to have is that, right, if you have a vector that's already along the x direction, if you project it along the x direction, you're going to get the same thing. But if you try to project it around the y direction, you're going to get 0, right? So hopefully that makes sense. So we're going to have some homework to deal with this. So you're going to get to prove, I'm not sure how many yet, but we'll get to prove, all. Well, I did 2 of them, so maybe we get to do the other 6 in homework. Okay. So one thing also to notice is that, so the one we did, I think, was this one and this one, right? The first 2, right? When you project the right chiral onto the right chiral eigenstates, right? You get the same thing back. The right chiral with the left chiral particle eigenstate, you get 0. Okay. But when you do the right chiral projection onto the right antiparticle, you get 0 instead. And this is because, right, the nature of the particle going to antiparticle is that you have this negative sign flips everywhere. And therefore that's how you end up with the opposite effect. Okay. In fact, right, the right chiral operator acting on the left antiparticle chiral eigenstate is the one that gives you the same eigenstate back. Okay. And you will see this when we work through some of this in the homework. Okay. All right. So this gives us, what's known as a basis, right? Whenever you think about basis, just think about it as x, y, unit vectors, right? That allows us to, express any state, right, in terms of both right and left chiral eigenstates, okay? So therefore, this is some arbitrary state, right? And this arbitrary state can be, have some right chiral component, right, along the right chiral axis, and then the left chiral component along the left chiral axis / eigenstate. Okay, right. And one neat trick we can do is that since these projection operator, this is PR, right, it's going to give you either the left and the right. You can actually insert these PR and P left in front of the eigenstates without changing the equation. And this is the trick we're going to do next. Okay. All right. So chirality in QED. Okay. So in the previous section, right, 6.2 and 6.3 actually, right, we found that, when we were dealing with particles, right, only the RL and the LR combination pairs are non-zero. By that I mean these current calculation that goes into the Lorentz invariant matrix elements. So remember, in order to calculate the cross section, we have to get this matrix element thing first, and this matrix element is calculated with these electron and muon currents dot producted together, the 4-vector dot product. Okay, and these currents are, have some particles adjoint spinors, right? So this is just U, E, gamma 0. Okay. And then you have this gamma matrix between the two, and then you have the other side of the electron current. Okay. So what we just learned right now, if we break these currents up into its XY component, its left and right chiral components. Okay, so I'm using this analogy too much, right? So for example, up here, right, let's just do this as an example. I know we don't calculate this, right? This is actually electron scattering, right? But, right, J, E, mu, right? This has some left and right components, right? So we have the adjoint, so some amplitude, right? R, U, E, R, right? UR, let's put the E afterward, for the one that's coming in, plus some amplitude, some component, sorry, not amplitude, some component on the left chirality ULE. Right, this is still P3, right? The same, we're just writing this side. Okay. Then we have the adjoint of this whole thing. And then we have gamma mu. I'm only going to write one of them. This is just to show you an example what this looks like, right? Okay. And then A, and then we also have the possible right-handed part. And these can actually be different, so I'm going to put a little prime here. Okay. The right-handed electron with momentum P1 coming into the vertex. Okay. Plus, right, the left-handed version of this, and also we put a little prime here, just because it is possible for it to be different. ULE P1, right? So when you're calculating these currents, right, that's where you end up with, you know, all these different combinations, right? You have basically 4 different combinations here, okay, for the incoming particle, okay? And then if you do the same thing for the outgoing, so in this case, I think this is calculating this electron muon scattering. So this one, the one we just did was for this vertex, right? The one we're going to write down. Oops, they're using cows here. Okay, right, that's for this vertex. So for this vertex, there's already 4 different combinations of chirality. And for this vertex, there's 4 different combinations of chirality also. Therefore, that's why we ended up with 16 times of that. But what happened is that when we do these, have these chirality projectors, what happened is that when you project these out, what happened is that a lot of the components end up being 0. And therefore, you know, we actually found that we only had to calculate 4 different back then helicity combination as opposed to having to do all 16. Okay. So what we can do is insert these respective chiral operator into these current. Okay. So just to show you an example of what happens. Okay. Remember, in fact, I'm just gonna box these, right? So this is gonna be useful, I think. And we'll see another one that's gonna be useful. Okay. So let's say we have the left adjoint, right, spinner. Okay. So so the left adjoint spinner, right, we can pull out this gamma 0 here, right, because that's the same thing, right? Remember, the adjoint is the same thing as whatever that is with the dagger, right, with the gamma 0 pulled out. Okay. So when we have this, what we can do is that, well, instead of, we're going to insert UL, since this is equal to PL UL, right? Actually, I'm not highlighting the right thing. PLUL, right? That's the same thing. Okay. Right. Therefore, we can insert that in there. Okay. PLUL, PL is actually 1/2, 1 minus gamma phi, right? Just the definition of PL. Okay. So the adjoint of that, right, due to the fact that, well, the identity matrix is its own adjoint, gamma 5 is also its own adjoint, gamma 0 is also its own adjoint. So this adjoint operation doesn't do anything except to UL. Okay, so we can pull that out. Whew. Okay. So now, right, what we can do is that use the anti-commutation relation. So whenever we flip gamma 5 with gamma 0, right, we just change the sign. Okay. Now, of course, gamma 0 is gonna, everything commutes with the identity matrix, right? So therefore, you can always commute with 1. Okay. So what happened is that when the left chiro adjoint can be written as the right chiro adjoint, but with the projection operator on the right hand side instead. Okay. Just to make sure, I think I missaid this. The left-handed adjoint, right, is the same thing as the left-handed adjoint with the right chiro projection operator on the right instead. Okay. All right. Doing the same thing for the other particle, right, meaning the other side of the current, UR. Okay. You're going to find that UR, right, is going to be basically PR UR. Okay. Actually, you don't even need to do that. Don't think that's the problem, because you can literally just do the substitution, right? Because PR UR is the same thing as UR, right? Okay, right. But using this results from up here, right, now we can plug in, right? We can replace UL adjoint with UL adjoint PR. So that's exactly what happened here. Okay, you still have this gamma matrix between the two for the current. So remember, this is J of some particle, right? This is the current, okay, that we found up here. Okay, right. So using the anti-commutation relation between gamma 5 and gamma mu once again, right? So gamma PR gamma mu, right? This is a 4-component 4x4 matrices, okay? Right, we'll plug this in here, right? That's what PR is, okay? Okay, what we're going to do is we're going to switch the order once again, right? When you switch the order, right, if it's anti-commutes, then you actually have a negative sign, okay? And then pull this gamma mu out in front, because 1 also commutes with everything once again. We see that, right? Gamma mu PR gamma mu is actually the same thing as P gamma mu PL, okay? So it's sort of interesting, right? Where when you pull these projection operators through these matrices, it changes basically the handedness of these chiro operators. Okay, you saw the same thing here where we basically pull the PL through these spinners and you get the opposite projection operator. Okay, so we end up with these two projection operators right next to each other, right? And guess what that's going to be? Okay. Right, so PL, right, is 1 minus gamma 5, right? And then, well, actually, I think we have this proof in the homework. So this is actually going to turn out to be 0. Okay, so I think that's a good little matrix multiplication exercise. Okay, so what happened is that, right, when you have a left chiro particle coming in, left chiro particle going out. So let me just draw this in the Feynman diagram, right? So we have, right, let's say we have this vertex here, right? So this is, let's make them electrons, right? Okay. So this is the part that represents this U adjoint L, right? Okay. And then you have a right handed particle, right chiro particle coming in. So, right, this combination is actually equal to 0, right? There's no way for this current to occur. Okay, so switching chirality from coming in and going out of the vertex is not allowed in quantum electrodynamics, okay? Which is sort of neat, okay? And you can do this for a bunch of other combinations. This sounds like a good homework problem, right? You'll see that whenever you have left a chirality changing particle to particle, you get 0, right? Chirality changing, antiparticle chirality changing, right? Between antiparticle and antiparticle, that's also 0. Okay, this when you have antiparticle to particle, right? Anti to particle, right? Changing is when they have the same chirality. That's when that is 0, right? Similarly with the right. Okay, so that's why when we did the electron positron annihilation, right? This one, let's say this one is VL adjoint, right? And this is UL, right? That's why this chirality combination has a current of 0 and therefore does not contribute to the Lorentz invariant matrix element. Oh, I have it down here. That was kind of silly. Okay. So when we go down, well, this is how, I want to make this connection back to section 6.2, right? When we did this calculation in 6.2, right, we drew the Feynman diagram, right? And then using the Feynman rules from chapter 5, right, we were able to write down all these different currents, right? And these different currents, right, when we do the algebra, now we're talking about abstract algebra, right? We found that, the current from an antiparticle to a particle, right, it is 0 if they are both left chiral and right chiral. Therefore, right, you can right away write down, right, the matrix element for L, right, as to anything, right, that's going to be 0. The matrix element for R, because these represents the incoming electron and positrons, right, to anything, that's also equal to 0. So it knocks out those 2 out of the 4 combinations right away, so you don't have to calculate it. Okay, so in hindsight, right, we saw that, this has to be the case, right, instead of computing all those gamma matrices previously. But I think Thompson was trying to get you guys to think about just utilize those 16 different combinations and just be glad that you don't have to do it. Okay, so now let's wrap up this section on just thinking about so we have this thing called helicity and chirality, right? And just let's review why they are different from each other, okay? So remember when we were computing the eigenstates for helicity, we have to use this assumption, or we have to go to this limit where it's very high energy, where the energy, right, of the particle is much bigger than the mass. Okay. This is where I should have wrote the other version. Let me grab that real quick. So I just grabbed these from chapter 6, chapter 4 also. Okay. Remember when we're computing the eigenstates of these helicity operators, right? In general, right, they have, square root of E plus M, and then you have this momentum part that changes, right? That's different from so for example, the up helicity, right, we have cosine sine, but then you have cosine sine, but then you have this P over E plus M in there. So the top half and the bottom half are actually different from each other. Okay. And it's only when we did the high energy limit, right, E much bigger than M, when we were able to basically simplify things by, well, E is bigger than M, therefore the square root in front just turns into E, back to red, okay? And then this P over E plus M also basically goes to 1, right? So therefore, the top half of the spinors and the bottom half of the spinors are actually symmetric with each other, okay? So, right? That was a simplification we made in order to simplify the calculation. Okay. So, however, you don't have to actually go to the high energy limit if we define things in terms of chirality eigenstates instead of the helicity eigenstates. Okay, so when we don't have this energy much bigger than the mass of the particles involved case, right? These up helicity particles, okay, have some normalization. That normalization is square root of E plus M, right? Okay, and then you have these, P over E plus M factor. The book decides to put this in as kappa now, okay, just to have another variable, okay. So when we apply, right, the, E much bigger than M limit, right, basically this becomes square root of E, which is exactly what you have here, right, and kappa basically becomes 1, right, which is exactly what we have in front. Okay, oops, I'm pointing to the down helicity one. Okay. So instead of defining these up helicity and down helicity state, if we define them as the right and left chiral state instead, right, we can have an operator, right, that operates on these left and right chiral states, where we have these properties where, if you do a projection along the right chiral direction, you get the same thing back. But if you do a projection, a right-handed right chiral projection along a vector that's only in the left chiral direction, right, you get 0. Okay, so we don't need this high energy operator anymore if we are using these chiral projection operators instead. Okay, where the chiral projection operator, right, if we to act this on onto the up helicity eigenstate, what we're going to get this factor of 1 plus kappa in the front. Okay, and that's because of this gamma 5 part. This, okay, and then, right, this E plus M, this P over E plus M factor also gets absorbed into this kappa factor. Okay, right, where if you were to act on the up helicity with the left projection operator, you don't get 0 exactly. Okay, that's because, right, we're not at the high energy limit, and therefore P over E plus M is not just 1. Therefore, you get a little bit of kappa. You get a factor of 1 minus kappa instead. Okay, where, remember, when kappa, right, is equal to P over E plus M. Okay, so remember, in the high energy limit, this goes to 1. Okay, so in the high energy limit, right, if kappa goes to 1, this whole thing goes to 0. And therefore, in the high energy limit, right, the helicity up eigenstate, when you project to the left chiral state, you get exactly 0. But if you have the up helicity state and you project to the right chiral projection, then you get exactly, well, you get 2 here, but then this cancels out the 1/2, so you get the same eigenstate back. Okay, so this is just the connection between helicity and chirality. Okay, so in general, right, a particle helicity can actually be written in linear combinations of these right and left chiral eigenstates instead. And these are going to be proportional to whatever you are, the right chiral helicity, right, with this 1 plus kappa in front of it, right? And then 1 minus kappa in front of the left one if we're starting off with the helicity up state. The opposite is true if you start with the helicity down state. So you're going to get, you're going to swap basically the R and the L. Okay. Okay. And once again, right, in the high energy limit where kappa is basically 1, right, then this just turns into U up, right, basically turns into UR, and then U down basically turns into UL. Okay. Just to make sure that, we're actually seeing this in real life, right? Remember when we did the cross-section calculation of helicity in the high energy limit, right? We came up with this 1 plus cosine square function in our differential cross-section, right? This is using high energy limit with helicity, right? Okay. In this calculation, right, we found that it's this 1 plus cosine square. That's actually this solid line here. Okay. Remember, notice that they're both get to the same spot in both ends. Okay. The data, the best fit of the data, let's do that in green, right? Right. So if you look at these data points and you try to fit a line through it, it's not exactly cosine square. Sorry, 1 minus cosine square. Sorry, 1 plus cosine square theta. Okay. This is skewed, right? Because we made this high energy limit approximation. Okay. So chirality, right, is always conserved, and therefore you can use it all the time, but the calculation is a little bit harder, right? Where helicity is conserved only in the high energy limit. Okay. So that's this difference between these two.